Welcome to this next video in the playlist on field theory. In this video, what we're going to talk about is an important little theorem regarding field extensions, which is often called the Tower law, or the Tower rule, or the Tower theorem. Okay, right, so let me firstly start by stating what the Tower law says, and then we'll prove it. Okay, right, so the Tower law is about having two field extensions. Okay, so what we're going to say is that we're going to initially have a field extension K, which is a field extension of a smaller field, capital F, but then we're going to have another field extension, an even bigger field, which is a field extension of K, so K is going to be a subfield of L. Okay, so drawing a picture for this then, let's have the largest field extension, which is L, represented by this large box here. So this is going to be L, and I'll color code this in. So here is L in green here, so that's L there, and then we'll have K as a subfield of L. So let's say that this portion here is going to be K, and we'll color in K in orange here. So this is our subfield of L, which we're calling K, and then even smaller we have F, which is a subfield of K. So here is going to be F, this tiny little one here. Okay, so we've got three different levels of fields basically. K is a field extension of F, and L is an even bigger field extension of K. Okay, so what then does the Tower law actually say? Well, the Tower law is all about this. The Tower law says that the degree of the field extension L over F is equal to the degree of the field extension of L over K times the degree of the field extension K over the field capital F. That is the statement of the Tower law. It's all about saying what is going to be the degree of this largest field L over the smallest field F, and you can get this if you know what the degree of the field extension L over K is, and you know what the degree of the field extension K over F is. So this is what I will mean by the Tower law, and this is what we're going to try and prove in this video. Okay, so the first thing to say is that if you consider the degree of a field extension over the smaller field, so if you consider, for instance, the degree of K over F, there are two possibilities. This can either be a natural number, okay, so a counting number, 1, 2, 3, 4, 5, 6, etc., or it can be infinity. Okay, so a field extension can be infinite, in which case the dimension of the larger field, viewed as a vector space over the smaller field, is infinite. Okay, so there are two possibilities for the degree of a field extension. It's finite and is a natural number, or it's infinite. Okay, now this law works with either of these cases. Okay, so either if it's finite then it works, or if it's infinite it works, with a little bit of bending of course. Okay, so we know that the natural numbers, the counting numbers, has a natural addition law and a multiplication law defined on it. What you can really imagine doing is sticking in the symbol infinity into the natural numbers, and then just saying, okay, we're only caring about multiplication here, let's just define any natural number to multiply with infinity to give infinity back again. Okay, and this Tower law does still work if one or both of these is infinite. So let me state that more precisely now then. So if both of the field extensions, if both the field extension K over the field F is a finite field extension, and let's say it has degree little n, and let's say L is a finite field extension of K and it has degree n, then the Tower law says that the degree of L over F will be finite, and it will be m times n. If, on the other hand, one or both of these is infinite, okay, so if, for instance, the degree of K over F is infinite, then it doesn't matter whether the degree of L over K is finite or infinite. What the Tower law will say is that the degree of L over F is going to be infinite, and we will prove that that is true. Okay, so that the Tower law does hold in that case. On the other hand, if it's the case that the degree of K over F is finite, and the degree of L over K is infinite, then again, the degree of L over F will be infinite, and again the Taylor law will hold. That's what I mean precisely by saying that the Taylor law works whether the degree of L over K and the degree of K over F are finite or infinite. Okay, right, so let's start off, however, by proving that it's true in the finite case, which is the case, you know, where it's very solid, and then we'll go on to the infinite case and explore that in a bit more detail. Okay, so let's start off with the finite case. So we are now assuming that both of these field extensions are finite field extensions. So the degree of K over F is some finite value, which we're calling little n here, and the degree of L over K is some finite value, which we're calling m here. Okay, now what that means is that we can find bases with these numbers of vectors in for these field extensions viewed as vector spaces over the smaller field. Okay, so let's do this. Let's start off with L over K here. Okay, so the degree of L over K is m. That means that if you view L as a vector space over K, so remember the picture here, we're viewing L, our largest field, as a vector space over K, then we can find a basis for that vector space which has m elements in. Now let's do that. So let's say the basis for L, which I'll just call B here, contains these m elements in, which we'll call V1 for vector 1, V2, V3, all the way up to Vn. Okay, so let's say this is my basis for the vector space L viewed as a vector space over K. Okay, so this is my basis for L over K. Right, and I can do a similar thing for, oh, and I should just say, all of these elements, the VI's here, they are all elements of the largest field L. Okay, and as I say, they will span and be linearly independent when viewed as a vector space over the field K. Okay, now let's do a similar thing for the field extension K viewed as a vector space over F. Okay, so again we can devise a basis for the field extension K viewed as vector space over F, and we'll call this basis C. Okay, and this will contain little n vectors, so we'll call these W1, W2, all the way up to Wn, and this time all of these WJ's, let's use a different index, you'll see why that's important in a moment, or why at least it's a good idea. So we'll call all the WJ's are going to be in the field extension K. Okay, so they're all going to be in the field K. Right, so I want to now show that the degree of L over F is equal to n times m. Okay, so I need to find a basis for the vector space L over F, which has m times n basis vectors in it. Okay, so here is my claim, and this claim will allow me to conclude that my claim is that a basis for L viewed as a vector space over F, which I will call D, okay, so just working my way down the alphabet, so here's my claim, that D, which is the set that is going to contain every possible combination of one of these multiplied with one of these. Okay, so it's going to be all things of the form, let's say, Wj times Vi, where I is equal to 1, 2, all the way up to m, and j, and I'll just put an and symbol there, j is equal to 1, 2, all the way up to n. Okay? So you can take any one of these, multiply it with any one of these, stick every possible combination into this set. I claim that this is a basis for the field extension L viewed as a vector space over K. Now of course, sorry, not over K, over F. Now of course all of these elements are going to be in the largest field, capital L. You're just multiplying elements that are in K with elements that are in L. Everything that's in K is in L, so you're just multiplying two elements of L together basically, to get a bunch of elements that are in L. So they are all elements of L, okay? And my claim now is that this actually forms a basis for the field extension L viewed as a vector space over the smallest field F. And of course, if that's true, then it's obvious then that the degree of L over F is going to be m times n, because it's just going to be how many elements do you have in this set that is the basis, and how many elements are we going to have in here? Well, there's n possibilities for how many W's we can pick, and there's m possibilities for the v's, so how many overall is in this set, so the order of this set is just going to be n times m, and therefore the degree of L over F would be n times m, i.e. the degree of L over k, which is this one here, times the degree of k over F. Okay, right, so we just need to show that this is a basis. If I can show that this is a basis, and I'll just write this, is a basis for L viewed as a vector space over F, so is a basis for L over F. If I can show that this is indeed a basis for L over F, then I'm done. Okay, I can conclude that the Tower law does work in the finite case. Okay, right, and it also gives me a lot of insight into this larger vector space structure where you're viewing L as a vector space over F in terms of the vector space structures, well, the two intermediate vector space structures here. Okay, right, so to show then that this is a basis, we need to show two things. We need to show that firstly, it spans the entire field extension L, where we're taking the coefficients from the field capital F, and we also need to show that it's linearly independent. So let's start off with spanning, because that's generally easier, and also once we've done spanning, it will give us intuition for how we can prove linear independence. Okay, so I want to firstly show that this spans L. Okay, so I want to be able to take an arbitrary element of L and show that it can be written as a linear combination of these basis vectors, or basis vectors to be. Okay, right, so let's take an arbitrary v, okay, so sticking with vector space notation, let's take an arbitrary little v, which is an element of our largest field, capital L here. What I now want to do is find some linear combination of these basis vectors where the coefficients are from the smallest field, capital F, which will give me v. Now, this might not be instantly obvious, but what can we actually do? What do we know we can do? Okay, we know that these vectors over here, the vectors v1, v2, all the way up to vm, are a basis for L over k. Okay, so if you give me an arbitrary v, which is an element of L, I can write this v as a linear combination of these basis vectors where the coefficients are from the field capital K. That is at least a start, because your intuition should be this, that if we can do that, well, we know that we can write any element of K as a linear combination of the basis vectors here, okay, where the coefficients will be from F, so maybe we can replace those in and everything might work out, and indeed it will. Okay, so that's what we're going to do. So we're going to start by writing V then as a linear combination of these basis vectors where the coefficients will be in the intermediate field K here. Okay, so I will just do this with the grown-up notation, so we'll have the sum from I is equal to 1 to n, okay, and then we'll have coefficients AI times the vectors vi. And remember, I'm not going to start denoting the additions and the multiplications in different colours, because all of these additions and all of these multiplications are just as they are in the largest field, capital L. Okay, because the other two fields, K and F, they are just subfields of that. Okay, so all of the additions and multiplications we see will just be addition and multiplication in the largest field, capital L. Okay, so I can write any vector, an arbitrary vector v, in the largest field, capital L, then, as a linear combination of these basis vectors where these coefficients, the AIs, I know that they have to be in the subfield, capital K, so I've got some restriction on where they actually are. Okay, so they're not just arbitrary elements of L, they're specifically in that subfield, capital K here. Okay? So it's possible to do that because, after all, we can view L as a vector space over K, and that vector space will indeed have m basis vectors, because we started with the initial assumption that the degree of L over K was finite and it was equal to m. And I should stress again that at the moment we're just doing the finite case. We'll come back to the infinite case later on. Okay, so we're proving the Tower law where both of these are finite, so we've started with that initial assumption. Okay, right, so where to next? Well, the idea now is these elements, these coefficients, are all elements of capital K. Okay, we don't like those. Okay, we like the VIs, they're looking hopeful because they're part of the basis vectors to be over here. Okay, so we'll leave the VIs, but we don't like the AIs, so we'd quite like to get those away. Okay, how can we do that? Well, we can write them as linear combinations of the basis vectors w1, w2, all the way up to wn, where the coefficients are going to be from our smaller field, capital F. So now what I can do is I can write the AIs as linear combinations. So the sum from j is equal to 1 this time to n of, and now I'll need coefficients with a double index, so I'll call these b's, bij, okay, of the wj's. So the I here, the first index, that corresponds to this I here, so you choose which AI you're talking about. I can vary from 1 to m here, and I'll just put that down. I is equal to 1, 2, all the way up to m. Okay, once you've set your I, that one will then be set, and the j then varies with this sum, and you're summing over j, from j is equal to 1 to n. Okay, so I hope you're comfortable with the double index there. Okay, it's just nice, convenient notation to use here. Okay, now of course what we can do is we can substitute in for AI these linear combinations of the w j vectors. Oh, and I should stress, I haven't stressed the important thing now, these bij's, these coefficients, are going to be from the smallest field, capital F. Okay, so this is all looking nice. I can now write my coefficients here, which were from the intermediate field, capital K, as linear combinations of these basis vectors, where the coefficients will be from my smallest field, capital F. So now I'm going to substitute this thing in for AI, and then just see if I can modify it into a linear combination of these basis vectors, where the coefficients are from the field, capital F. And indeed I will be able to do that. So this will become the sum from I is equal to 1 to m. Okay, and I'll just move this up a little bit. Okay, the sum from, and I should just initially put brackets around this, the sum from j is equal to 1 to n of bij wj times each vi. So this is now taking the place of that AI. I've just substituted it in here. Now, of course, we can apply the distributive law, okay, because this entire great big sum is just being multiplied by its respective vi here. What I'm going to do is just apply distributivity and turn this into a great big sum. So this will become the sum from I is equal to 1 to m, the sum from j is equal to 1 to n, and then we'll just have all of these terms, bij, wj, vi. So now this just means take all of these terms where I can vary over 1 to m and j can vary over 1 to n, and add them all together, basically. Okay, right. So we now end up with this thing here. Okay, right, and that's exactly what we want. This is a linear combination of these basis vectors to be here. It's a linear combination of the elements in this set here. Okay, these coefficients are all from the field capital F, okay, and they're all just in front of all the different basis vectors here. So we have just got this arbitrary element v in our largest field, capital L, written as a linear combination of the vectors in this set. So this is all looking good. So we can now conclude that this set of elements of the largest field, capital L, does indeed span the entire field L when you take linear combinations over the field F. Okay, excellent. So now what we want to prove is that it's linearly independent. Okay, so linearly independent. So what we want to now prove is that if we have a linear combination of these elements of the field capital L, and I will just call them vectors, if we have a linear combination of these vectors where the coefficients are from our field capital F, that equals the 0 vector in our vector space L, which is of course our field extension, then it has to be the trivial linear combination. Okay, so let's show this. So let's suppose that we do indeed have such a linear combination. So we're now going to have the sum from I is equal to 1 to m, the sum from j is equal to 1 to n of bij, wj, vi, okay, equaling 0, where the bij's are all from the field capital F. So this is just a linear combination of these vectors in this set, my basis to be, and I'm saying that it is actually going to give me 0. What I now want to prove is that all of these coefficients have to equal 0. I want to prove that all the bij's are equal to 0 necessarily, okay? Because that will then prove that the only linear combination which satisfies this is the trivial linear combination. So how can I do this? Well, I'm going to do what I did here in reverse, basically. I've got, at the moment, a linear combination of these basis vectors to be. Okay, what I want to do is turn it back into this form. So I'm going to factor out the VI's. I'm going to collect together all the terms which have the same VI in. Okay, so whether I is a certain element from 1, 2, all the way up to m. Okay, and I'm going to collect the terms with the same VI's together and factorize out the VI. And of course, what I'll turn this into is the sum from I is equal to 1 to m, and it will go back into what I've got here. Okay, the bits that I'll get are all of these different coefficients, if you like, here. So I'll get the sum, and I'll just move this up a little bit. The sum from j is equal to 1 to n, bij, wj, and all of that will now be in front of the VI. So I've just collected together all of the terms with the same VI's, and all of the terms will have different j's. So I have j is equal to 1, j is equal to 2, all the way up to j is equal to m. I've collected all of those together, factorized out the VI, and then I've just got the sum of these bits that were in front of the VI's, which is exactly what I've got here. The sum from j is equal to 1 to m of bij, wj. Okay, so that's what I've done here. I've factorized out the VI's. The reverse of what I did here, basically. Okay, now, because these wj's are, of course, the basis vectors for k viewed as a vector space over f, and because these bij's are elements of f, this is just a linear combination of those basis vectors, so I can conclude that these things here, okay, are elements of the intermediate field k. Okay, and I might as well now start calling them ai's. Okay, so if you do that, then what you've got is the sum from I is equal to 1 to n, ai, vi, and you see we really are just going in reverse here, which is why this argument was best done first, so that we can see that we're just going in reverse from there. Okay, and we know that these ai's are just elements of the field capital K, the intermediate field. Okay, and we know that this thing is going to equal 0. But look, we now have a linear combination of these basis vectors, the VI's, where the coefficients are from the field capital K, okay, which is giving 0. Now, because the set V1, V2, all the way up to Vm was a basis for the largest vector space L, sorry, the largest field L over the intermediate field K, then we know that the only way that you can take a linear combination of those basis vectors and get 0 is if all of these are equal to 0, all the coefficients are equal to 0. So now what I can conclude is that ai is equal to 0 for all I is equal to 1, 2, all the way up to m here. Okay? So you can conclude that, because otherwise it wouldn't be true that those basis vectors v1, v2, all the way up to vm were linearly independent. Okay, but now let's remember what that actually means. That means that all of these sums are equal to 0. So now I can conclude that the sum from j is equal to 1 to n, bij, wj is equal to 0 for all the i's. So all these different sums where you have a different I there, they're all equal to 0. Okay, but now remember, these vectors, these wj vectors, these were a basis for the intermediate field K viewed as a vector space over F. The bij's here are in the field capital F, so this is just a linear combination of those basis vectors, okay, in K. Now, because these are supposed to be linearly independent, we know that the only way that we can take a linear combination of these basis vectors and get 0 is if all the coefficients are equal to 0. So that now tells us that bij's are equal to 0 for all the j's. Okay, and now since we already know that it's the case for all the i's that they're equal to 0, we now know that bij is equal to 0 for all I goes from 1 to all the way up to m, and for all j goes from 1 to all the way up to n. And I'm sorry, that's a little bit cramped down there. Okay, so by breaking it up into this way, we can conclude that all of these coefficients have to be equal to 0 because of the fact that those basis vectors that we use to construct the basis vectors in this set D are linearly independent. So indeed, we now have shown that this set of vectors in the largest field L is in fact linearly independent, and it also spans the entire of L, where we have these coefficients from the smallest field, capital F. So indeed, this is a basis for the largest field L viewed as a vector space over the smallest field, capital F. Okay, and therefore we can conclude that the dimension of that largest field extension L over the smallest field F is actually just going to be n times n. So there's the proof of the Tower law, where we're just dealing with finite field extensions, so where both of those intermediate field extensions, the field extension from F to K and the field extension from K to L, are finite. We've then proven that the Tower law holds true there. In the next video, what we'll do is have a look at the infinite case and prove that the Tower law still holds true.